So in terms of what we're covering today, we're covering trig stuff. And we'll be covering that this entire unit. So this entire unit will be trigonometry things. So angles in a circle, angles of triangles, all that kind of good stuff. And then we'll do some trigonometric identities as well. This covers a lot of material. Covers chapter 5, chapter 6, chapter 7, and a bit of chapter 8 as well. So there's a lot of chapters here, but it all is dealing with the same core topics in different ways. Okay. All right. So let's get started. This first chapter, chapter 5, will go fairly quickly, I'm guessing. And yeah, hopefully it will. But once we get to chapter 7 with the trig identity stuff, that gets a little bit trickier. And I'll talk about that when we get there. So the first thing we're going to cover is angles. Okay. An angle is made with two rays from the same endpoint called vertex. Okay. So a lot of times when we symbolize angles, we do so with Greek letters. So maybe the most common one we use is theta. That looks kind of like an O with a line through it when you draw it on the board. When I draw it on the board, that line will be sort of at the top of the egg there, shape. Phi is another angle you'll see. Phi can be actually written in two different ways. Looks like a circle with a slash through it, or looks like a script circle with a slash through it. Okay. Like somebody drew it real quick, you know. So that's phi. Alpha, beta, and gamma are also angles that we'll deal with. And you can see those are a little bit more straightforward. So oftentimes we symbolize with Greek letters, as you can see here. Okay. So what is an angle? An angle is where two rays intersect. We are going to measure those angles by measuring the amount of rotation needed to go from an initial ray to a terminal ray. So an angle measurement is the amount of rotation. So we have to designate one of these rays as our initial and one of them is terminal, and how much rotation it takes from that ray to rotate up and become the other ray is our measurement of the angle. So it's a measure of rotation in this case. So we have to have some sort of a standard level of rotation that we can use. And there's two measures of rotation. We can measure in degrees, or we can measure in radians. And we will go back and forth with both throughout this unit. Sometimes we'll use degrees, sometimes we'll use radians. With degrees, a full circular rotation is 360 degrees, And then any partial rotation is whatever percentage that is. So if I do a quarter of a circle, I do a quarter of 360, that'd be 90 degrees. In the same way, a full circle rotation in radians is 2 pi radians. And it works in the exact same way. If I have a partial rotation, like a quarter of a circle, that'd be 2 pi over 4, which is pi over 2 radians. Okay. So, everybody understand what I mean by full circle? Let me just write what I'm talking about. If I start with my initial ray there, and I take that thing, when I'm talking about a full circular rotation, I'm saying we take this initial ray and we rotate it all the way around till we get to here. Usually we draw that there. If we do a full circle and it comes back to the start, where my terminal ray is the same as my initial ray, that rotation, that's why I call it full circle, goes all the way to circle, then that is 360 degrees or 2 pi radians. By the way, this means that any partial measurement, like if my initial ray is there, and I go on half of a circle, so my terminal ray goes out on the exact same line. Since that's a half of a circle, that would be 180 degrees or pi radians. Does that make sense? And then a quarter of a circle would be 90 degrees or pi over 2 radians, and et cetera, et cetera. Okay. Now notice that I have my array pointing to the right. My initial ray pointing to the right. That's the standard position when I draw things on the XY coordinate plane. When I draw things on the coordinate plane, the standard position of the initial ray is starting at the origin and pointing to the right on the x-axis. So if we have an XY grid, the standard position of the initial ray is starting at the origin, pointing to the right along the x-axis. And then when we do rotation, a positive rotation is a counterclockwise rotation. This is what I drew on the board. This is how I rotated it when I was doing that. So a counterclockwise rotation is a positive rotation. And a negative rotation would mean I would go clockwise from my initial ray. So positive rotation and negative rotation is down. Now, degrees I'm sure that you've dealt with before, radians you've probably dealt with as well. But I just want to point out something about radians and the fact that a full circle is 2 pi radians. A full circular rotation is 2 pi radians. So full rotation in radian measure is equal to 2 pi. And you may think, well, wait a second, the circumference of a circle is 2 times pi. Okay. And it turns out that arc lengths of circles are connected to radians. You guys know what I mean by arc lengths of a circle? So if I draw a circle centered at the origin, let's just say of radius r. Short, but that's okay. So think of this. The radian measure of an initial ray starting here and going around the circle all the way gives me a radian measure of 2 pi. If I take this point and move it around the circle, all the way around the circle, the distance it's moved is the circumference, which is 2 pi times my radius, whatever my radius is. Okay. If I move a quarter of the way around this circle, then the length that I would have moved is, well, I would have moved pi over 2 radians, that's a quarter of 2 pi, times r. We follow that, times the radius. So whatever arc length I move around the circle is going to be my radian measurement of rotation times r. Okay. So the arc length is radian measure multiplied times radius of circle. So if I go from here, let's go from just to there to there. Whatever radian measure that is, times the radius of the circle, gives me this length here. Okay. So if you wonder where the 2 pi comes from and why we measure radians in terms of pi, it's because it's this connection to the arc lengths of circles. Does that make sense? So that's why radian measures are the way they are. Now, degree measures are different. Degrees are 360. That's kind of a, I wouldn't say arbitrary, but that's a numerical value that is based in history. Okay, 360. degrees is not necessarily, I mean, it's connected to the circle, but it's not connected to the arc length of the circle in a straightforward way. Okay. If another culture would have come up with measurement in degrees, we might have had a different measurement. We might have had a circle measured in 100 degrees if it came out of a base 10 culture. But it comes out of a base 6 culture, you end up with 360. That makes sense for base 12. Now, what we're going to do for just a moment is talk about converting. So we see where radians come from. We know that degrees are 360 degrees in a circle. This means that if I want to go back and forth from degrees to radians or vice versa, then since I know 360 degrees is 2 pi radians, and like I wrote on the board, 180 degrees is pi radians. Remember, that was a straight line. You can use either of these two to convert back and forth. The general one that we use more often is the 180 is pi radians, then you don't have to deal with the 2. Okay. So when you go back and forth, we just have to use the fact that 180 degrees is pi radians and just do a multiplication, division to go back and forth. So let's take some degrees and convert them to radians. So we're going to take some measurements of angle rotation in degrees, and we're going to convert into radians. We got 42 degrees, 217 degrees, negative 51 degrees, and 324 degrees. We'll convert the other way in just a moment. So we know 180 degrees is pi radians. Okay. So what we do, anytime we want to go from degrees to radians, I multiply by a fraction of 1. So I'm going to multiply by a fraction of 1. And we do so that the degrees cancel out and we're left with radians. So since I have 42 degrees, I'm going to put 180 degrees on the bottom. That way degree and degree will cancel each other out. And then pi radians on the top. So the degrees will cancel each other out, and I'll be left with radians. Everybody get that? These are just labels. They work just like variables. So 42 times pi over 180 radians. And I probably simplify that. I don't know what that is. 42 over 180 simplified is 7 over 30. So that's 7 pi over 30 radians. That's my exact value. If I want an approximate value, then I just type in 7 times pi over 30, which is about 0.73. That makes sense? Yes. Have you converted like that? Multiplied by a fraction of 1 And then if I want to convert from degrees to radians, degrees on top and bottom cancel each other out. Radians are left behind. Okay. So that's what I like to do. And you can do this for each one. Once you get quick at it, you'll write less and less. So 217 pi over 180. I don't know if that's my radians. 217 pi over 180. Is about 3.79 radians. This would give me a negative 17 pi over 60 radians. When I simplify that, which is about negative 0.89. This is 9 pi over 5. When I simplify that, it's in radians. That's about 5.65 radians. I'm just using my calculator to convert to simplify those improper fractions. That makes sense. Does that make sense? So just type in negative 51 over 60 and then have your calculator put it into an improper fraction of negative 17, or in this case, proper fraction of negative 17 over 60. In this case, an improper fraction of 9/5. But there you go. Pretty straightforward, not too crazy. We can do the same thing in reverse as well. By going from radians to degrees. I want you to try this on your own. Now that we've went from degrees to radians, go the other way. Go from radians to degrees by using that 180 is pi, 180 degrees is pi radians. In each of these cases. All right, so since we started radians and we want to end with degrees, we're going to put the degree on top, 180 degrees, over pi radians on bottom. So we just flip that. So we change from the opposite ways. When you do that, in this case, you end up with 36 degrees. So pi over 5 radians is 36 degrees. When I take 5 pi over 3 and multiply it times 180 degrees divided by pi radians, I know I'm not writing the radians. I could put radians, and show you that those cancel out, right? Those labels cancel out. But that becomes 300 degrees. Multiplying by 180 degrees divided by pi radians, pi's actually cancel out, and we get negative 18 degrees. So negative pi over 10 radians is negative 18 degrees. And then this last one, we multiply times 180 degrees divided by pi radians. Since this didn't have a pi in it, it's going to come out to be irrational. And we get about 101.99. That is degrees. Okay. So going back and forth between radians and degrees should be fairly straightforward. We're multiplying by a fraction of 1. And depending on whether we're going from degrees to radians or radians to degrees, we're multiplying by pi over 180 or 180 over pi. And I always think when I do that, we're canceling out labels. So the label I want to cancel goes in the bottom. The label I want to keep goes in the top. Now, there are some really common angles that we'll use over and over. And especially once we get to the unit circle stuff, these 3 angles show up time and time again. I shouldn't say that it's just these 3. There's these 3, and then the quadrants. And I'll talk about the quadrant angles in just a second. Okay, the angles that break up the Cartesian coordinate plane into quadrants. So let's deal with the 30 degrees, the 45 degrees, and 60 degree angles. And then we'll talk about the quadrant angles as well. All right. You guys know what I mean by quadrants? We've done this before, but I'm talking about the Cartesian coordinate plane broken up into a quadrant 1, 2, 3, 4, just like we've already, we see that when we graph anything. So I'll go over that as well. So 30 degrees, take pi over 180 And if I take 30 over 180, I get 1 out of 6 or 1/6. So this becomes pi over 6 radians. So 30 degrees, I'm just going to write this in the shorthand. 30 degrees, pi over 6 radians. You can do the same thing with 45 degrees. Multiply it times pi over 180. 45 divided by 180 is a quarter. So 45 degrees is pi over 4 radians. You can do 60 degrees in a couple of different ways. One is you can just say it's double 30 degrees. Or you can do the times pi over 180. Either way is fine. So if I double 30 degrees, doubling this, 2 pi over 6 is 1 pi over 3. So 60 degrees is pi over 3 radians. Now, in terms of these angles on my quadrant, I think of rays going out along the x-axis and the y-axis. If a ray is going along the x-axis, that is 0 degrees, which is also 0 radians. If that makes sense. As I start to rotate that, I end up hitting the y-axis. That's a quarter rotation of the full circular rotation. So that quarter of 360 is a 90-degree rotation. So that's going to be a 90-degree rotation, which 90 degrees is half of 180. So as far as radians, that's going to be pi over 2, half of pi. Once we do a full line, and we're going out on the left along the x-axis, that's 180 degrees, which is pi radians. We've already established that. Going another quarter rotation is going to be 180 plus 90. So that's 270. So that's 270 degrees. Pi over 2 plus pi is 3 pi over 2. Or I'm thinking of 1.5 pi's. So 3 pi over 2 radians. And then if I continue my rotation, I get back to my starting line, which would be 360 degrees. Or 2 pi radians. So my quadrant angles are 0, 90, 180, and 270 degrees. Or in radians, 0, pi over 2, pi, 3 pi over 2, 2 pi radians. Okay. Those break up that Cartesian coordinate plane into the 4 quadrants. So any angle between 0 degrees and 90 degrees will be in quadrant 1. Any angle between 90 and 180 will be in quadrant 2, and so on and so forth. Notice that these three, the 30, 45, and 60, those were all in quadrant 1. And moreover, if you think about 45 degrees splits this quadrant, halfway in between. It's the half measure of pi over 2. Half of 90. So we go 45, another 45. And that's why it ended up with pi over 4 radians. Half of pi over 2 is pi over 4. Half of 90 is 45. Okay. And if you think about the 30 angle measurement, that splits it into 1/3, 2/3 sections. Okay. And if you think about 1/3 of pi over 2, that's pi over 6. And the reverse happens with 60. It goes 2/3, 1/3 of that first quadrant. Now, once you've established this, then you can say, oh, what about going at, for instance, this angle? This is like going 180 degrees plus an additional 30 degrees. So that's 210. Or pi plus pi over 6. That'd be 7 pi over 6 as an improper fraction. So we can get all of these different angles based on combining our quadrants plus these three. Adding and subtracting those three inside any quadrant. Now, just so that we have this, a lot of times it's really easy to see what quadrant an angle is in if we're measuring in degrees. If we're measuring in radians, because radians deal with these pi's, oftentimes it's not quite as easy to see what quadrant our angle is in if our angle is measured in radians. Does that make sense? So just so that we're aware, 0 degrees is 0 radians. The rounded to that is just still 0 radians. 90 degrees is pi over 2. The rounded version of that is about 1.57. Pi is about 3.14. The rounded version of 90 degrees is about 1.57 radians. Okay. 180 degrees, that's just pi, that's 3.14, 159, et cetera, et cetera. So the rounded version of that is about 3.14. 270 degrees is 3 pi over 2. We've seen that. That's about 4.71 radians. And then 2 pi is 360 degrees. That's about 6.28 radians. Okay, follow what we're doing there? So we're just establishing sort of these markers for where our cutoffs for quadrants are. Right? 90 degrees is about 1.57 radians. 180 degrees is about 3.14 radians. 270 is about 4.71. 360 is about 6.28 radians. So if we want to determine what or where the terminal side of the angle, what quadrant the terminal side of the angle is at, if we're given radians. So for instance, if I'm given 7 pi over 4 radians, there's a couple of ways to determine what quadrant the terminal side is on. Excuse me. Let me do this on the board. So let me write 7 pi over 4, that's radians. We'll also look at 2.11 radians. We'll look at negative 1.20 radians as well. And we'll determine there we go. Where the terminal side of the angle is on. Okay. Remember, the initial side of the angle is long as along the x-axis pointing to the right. That's our standard starting place for the angle. If we have 7 pi over 4 radians, if you think about that, that's like 5.50 rounded. Okay, just put 7 pi over 4. That's 5.50. Remember, pi radians is 3.14 radians roughly. 270 was like 4.71 radians roughly. 2 pi is like 6.28 radians roughly. So if we know 7 pi over 4 is about 5.5, we know it's somewhere between here and here. So I know it's going to be in quadrant 4, right? So I know this is going to be in quadrant 4. Because of the fact that it's 5.5 radians, and that's how we know what's going on. The other way I could have done that is I could have converted this to degrees. And saw that that's 7 pi over 4 is 315 degrees. And it's easy to see 315 is between 270 and 360. So again, we're in quadrant 4. So either way is fine to determine the quadrant. We can determine the quadrant based on where the radians are at. We can also determine the quadrant based on the degrees of where we're at. Same thing here. If I have 2.11 radians, remember pi over 2 radians was about 1.57. So 2.11 is more than 1.57, but less than 3.14. So I know it's going to be in quadrant 2. Okay, based on radian measures. if I did want to figure out which quadrant it is in based on degrees, then I could have just multiplied 2.11 times 180 divided by pi, and that's about 120.89 degrees. Which is obviously more than 90, less than 180. And so I know that's in quadrant 2. Or basically what I'm doing there, I'm doing 2 ways of finding what quadrant the terminal side is in. I'm using either my knowledge of radians or my knowledge of degrees. In this case, I just started out with knowledge of radians, then I converted it to degrees to make sure. You can do it the other way as well. Here's where it gets a little bit tricky, is when we have negative angles. When we have negative angles, we have to rotate in the opposite direction. So instead of rotating counterclockwise, we start rotating clockwise. So 270 degrees is 3 pi over 2 radians. But if I went in the negative direction, that's also negative 90 degrees. So that's negative pi over 2 radians. Notice it's the exact opposite of this. So that's negative 1.57 radians approximately. So if we're talking about going down 1.20 radians or negative 1.20 radians, that's not yet to 90 degrees, so I'm in quadrant 4. Okay, so it's quadrant 4. And in the same way, if we wanted to instead use degrees rather than radians, we could have just multiplied it by 180 over pi. That would have been a negative 68.75. Degrees, and we'd have got the same result. So whether we use degrees or radians, we can determine what quadrant we're in. And by what quadrant we're in, I mean the terminal side of the angle. The initial side is always pointing right along the x-axis. Any questions about that? Straightforward. This next slide we won't convert. We'll just look at the angle measurements and decide what quadrant we're in. So let's take a look at these. So we won't do the conversion from degrees to radians. If you want to, you can do that on your own. But let's just determine the quadrants based on the angles in degrees. So we have 112 degrees, negative 105, and then 450. There we go. So if we're not going to convert, we just say 112 degrees. What quadrant is that in? 2, exactly. So quadrant 1, quadrant 2. It's above 90, less than 180. So that's in quadrant 2. How about negative 105? What quadrant's that in? 3, exactly. So further rotation to negative 90, but not yet to negative 180. This would be negative 180 if I keep going. So between negative 90 and negative 180, we're in quadrant 3. Now here's a weird one in 2 different ways. 450 degrees is more than 360, right? So that means I do more than a full circle rotation. I go at 360 and then I keep going. Okay. Now, interestingly enough, how much farther do I keep going? Well, it's going to be the difference between 450 and 360. If I take 450 minus 360, that's 90, right? And so I end up at exactly this angle. So my terminal side is going to be exactly along the y-axis. When our terminal side is in between quadrants, we say that this 450 degrees has a terminal side that's not in a quadrant. Since it's along one of the axes, in this case, the y-axis. So if the terminal side ends up at the 0 degree, the 90 degree, the 180 degree, or the 270 degree marks, then we say we are not in a quadrant. Since we're on the axis, we're splitting between quadrants there. Does that make sense? Now, this brings up a point. Second thing. This brings up the concept of what's called a coterminal angle. Coterminal angles are 2 different angle measurements where their terminal side is the same. So for instance, we just saw that 450 degrees is coterminal with 90 degrees. Since their terminal sides are pointing in the exact same direction. This happens if we do more than a 360 degree rotation. So anytime we add 360 degrees, we've created a coterminal angle. So 90 degrees is coterminal with 450. If I add another 360, that becomes 810. So 810 would also be coterminal with 90 degrees with 450 degrees. Okay. Also, we could also subtract 360. So negative 270 degrees is coterminal with 90 degrees. I get that? I just took 90 minus 270, or minus 360 to give me 270, negative 270. So negative 270, 90, 450, 810 degrees are all coterminal angles. Their terminal sides are all pointing in the same direction. And we can do the same things with radians as well. We can just keep adding 2 pi radians over and over and over and create coterminal angles, or subtract 2 pi radians over and over and over and create coterminal angles. There will be times when we're dealing with angles in this unit where, to avoid the problems of coterminal angles, we'll just say assume the angle is between 0 and 360 degrees. And then give me the answer where the angle is between 0 and 360. Or give me the answer where the angle is between 0 and 2 pi radians. Something like that. So just like this. And if you ever want to do that, if you ever get an angle which is not between 0 and 360, but you want the angle between 0 and 360, you just have to add or subtract 360 degrees over and over and over until we get the right coterminal angle. So for instance, this says find the coterminal angle of the given angle such that the angle that I'm finding is between 0 and 360 degrees. So if I take negative 105 and add 360, I get 255 degrees. So I know that 255 degrees is coterminal with negative 105. And that 255 is between 0 and 360. So 255 is the angle I want there. I didn't write it on the board, but if I want to find a coterminal angle, just keep adding or subtracting 360 until our angle becomes between 0 and 360. If I take 450, this is what we just looked at, right? Instead of adding 360, I'd have to subtract 360 because that angle's too big. And that would be 90 degrees. So the coterminal angle of 450 degrees is 90 degrees. The coterminal angle between 0 and 360. Okay. You can do the same thing with radians. This one I will write on the board. Take 19 pi over 3 and create a coterminal angle between 0 and 2 pi. And then we'll do the same thing with negative 18 pi over 5. I'm going to show you kind of how I do this in my head, right? Oh, shoot. That's the one. Good. All right, so here's my calculator. Here's what I would do. So on the degrees, I just added and subtracted 360 till I got an angle between 0 and 360. Okay. With the radians, I'm going to do that as well. I'm going to take 19 pi over 3. Oops. 3. That is more than 2 pi. Remember, 2 pi is about 6.28. So what I'm going to do is I'm just going to subtract 2 pi and then subtract 2 pi again. And then subtract 2 pi again. And I keep subtracting 2 pi over and over and over until my answer is between 0 and about 6.28. Now that it's between 0 and 6.28, I know that the coterminal angle of 19 pi over 3 is about 1.0471975551. If you want to force that to be in exact form, something like pi over 3 or pi over 2 or whatever, you can just divide by pi. Notice that it's a nice decimal of 1/3. Okay. So 19 pi over 3 is the same coterminal angle. I should say it's coterminal with pi over 3. Now, there's another way to do this as well. And that is just to take and ignore the pi for a second. Okay. If I ignore the pi, 19 over 3 is 6.3 repeating. If I subtract 2 pi, ignoring the pi, I'm just going to subtract 2 over and over and over again. So that's going to be 0.3 repeating times pi as its coterminal angle. Everybody get that? So you can divide out pi initially, or you can just leave pi in. Just keep subtracting 2 pi until you get something between 0 and about 6.28. Yeah.
Could we technically also just, instead of doing 2 and 2, could we say minus 6 pi as well?
Absolutely. Yep. So it's perfectly fine if you see that, for instance, this is 6 1/3 pi, subtract 6 pi off of the whole thing immediately. Yep. I did it over and over for emphasis, but yes, you can absolutely take 19 over 3, see that it's 6, you can subtract in multiples of 2, and then do all that in one step. In a similar way, if I took negative 18 over 5, let's say I ignore the pi and negative 18 pi over 5. That's negative 3.6. I would add 2 pi and add 2 pi again to get something between 0 and 2. So that's 0.4 times pi as the coterminal angle. Or if you wanted to write that as a fraction, that's 2 pi over 5 as a coterminal angle. So just by adding 2 pi over and over and over again, you get to a place where you have 2 pi over 5. Does that make sense? Just by subtracting 2 pi over and over and over again, you get pi over 6, pi over 3. And you can do that in lots and lots of different ways. Like I said, I showed a couple of different ways on the calculator of how to do that. You can also do it just as easily by hand. Like for this one, negative 18 pi over 5. Think of 2 pi as being 10 pi over 5. So we can just add copies of 10 pi over 5 over and over again. And if I do that twice, that's going to be 20 pi over 5, which is going to give you 2 pi over 5, right? That makes sense? So, same thing here, 19 pi over 3, 2 pi. If I'm thinking about a denominator of 3, that's like 6 pi over 3. So if I take 19 pi over 3 and keep subtracting 6 pi over 3, 3 times, so 6 times 6 times 6 would be 18. (19 minus 18 is 1, so you get 1 pi over 3. So you can do it by hand, you can utilize your calculator, lots and lots of different ways. Okay, but main principle is you're just, in radians, you just keep adding or subtracting 2 pi, and a bunch of copies of that. Okay, oops. So that's the idea of coterminal angles. Coterminal angles are angles with the same terminal side. And in trig, a lot of times those are essentially the same things. Not always, but most of the time. All right. So that's the introduction to angles section. Once we've looked at angles, once we know what angles are telling us, then we're going to start looking at the unit circle. We'll start out with sines and cosines, and we'll really quickly transition to all the other trig functions. Okay. So when we talk about the unit circle is called the unit circle because it is a circle whose radius is 1. 1 is known as the unit in mathematics. So the number 1 is a unit. People often ask, like, why is 1 not a prime number? We don't consider 1 prime. It's divisible by 1 in itself, right? Only. But it's not prime because it's the unit number. Okay, so 1 is unit. And so we have a unit circle that's the circle of radius 1. And for sake of ease, we always start the unit circle centered at the origin. So our unit circle is always centered at the origin and of radius 1. The equation for that is the following: x squared plus y squared is equal to 1. So every point on that unit circle satisfies the equation x squared plus y squared is equal to 1. Okay. Every point is a distance 1 away from the origin. We understand why the equation has to be this way. Let me write that on the board just a second. Maybe, yeah, let me write that on the board before I hit the wrapping function. So imagine that I'll start in the first quadrant. Imagine I have a point which we call x, y on the unit circle. So my x value is here. This is the origin, obviously. My y value is here. We're asking what is the distance from, well, we're asking what relationship the x and y has to have. Well, there's a right triangle implicit in the unit circle. Everybody see that? And the length of this leg of that right triangle is obviously x. The length of this leg of the right triangle is y. And since we have a circle of radius 1, the length of the hypotenuse has to be 1. And so based on the Pythagorean theorem, here one leg is x, one leg is y, and then the hypotenuse is 1. A squared plus b squared equals c squared. A is x, b is y, c is 1. So we have to have x squared plus y squared equals 1 with every point. And that works very well in the first quadrant. You can imagine if we go to the fourth quadrant or the third quadrant or the second quadrant, we might have a negative y value, but that's fine because squaring it gives me a positive. Or a negative x value, that's fine. Squaring it will give you a positive. But no matter what point on the unit circle we have, it has to satisfy that equation. Even when the x and the y values are negative, like in the other quadrants. So that's why the unit circle has the equation it does. X squared plus y squared is equal to 1. Now, what we're going to do is we're going to associate a point on the unit circle with an angle, and that angle is going to be such that the terminal ray of that angle is going to intersect the circle at point x comma y. So I'm going to take unit circle and I'm going to have an angle whose initial ray is the x-axis, pointing to the right, and whose terminal ray is something other. But the terminal ray is going to have to intersect that unit circle at some value, some point. Okay. So whatever angle this is, we're going to call this the Greek letter theta. And we're going to introduce this wrapping function where if I input any angle, the terminal ray is going to intersect the unit circle at some point. That point will be my output. So we input an angle and we get an output point, right? That's a little bit different than we usually do. Usually we input a number, we get out a number, single number. Here we input a number and we get out a point, an ordered pair. Now, because of the picture that I had drawn earlier, with the x values and corresponding x values and y values, we can figure out certain ordered pairs for certain angles. So if I input an angle, I should be able to find an ordered pair. At least for some of these. So for instance, if I said, what is the wrapping function when I input 0? Now we're going to input either in radians or degrees. Right now we're inputting in radians. Do I follow that? So we're inputting in radians. So 0 radians. And then I'll do pi over 2 radians. And then I'll input pi radians. And then I'll input 3 pi over 2 radians. And then 2 pi radians. These are my quadrant angles. Do you follow that? These are the angles there. So if I'm at 0 radians, then we're going to intersect the circle at the point 1, 0. Right? That's the point 1, 0. Right there. So that's it. When I input 0, I get 1, 0. When I input pi over 2, then I'm at this point, since this is circle of radius 1, this is 0, 1. Right? It's a point along the y-axis, 1 unit away from the origin. So it's the point 0, 1. When I input pi, I'm on the x-axis left. So I'm left on the x-axis, 1 unit away from the origin. That'll be the point -1, 0. How about 3 pi over 2? 0, -1, exactly. Yeah, we're 1 unit away down along the y-axis. So we're at the point 0, -1. And then when we go to 2 pi, my terminal angle, yeah, it's the same thing as 0, right? So the wrapping function is also going to give me 1, 0. And you can see now that if I have 2 angles that are coterminal and I put them into the wrapping function, they're going to give me the same points out. Right? So if 2 angles are coterminal, I'll call it alpha and beta. If alpha and beta are coterminal, then the output of the wrapping functions are going to be the same. You can see that that's going to be the case no matter what angle you use. What about the three other angles that we said were going to be special? Could we find the wrapping function? If I'm talking about in degrees, something like 30 degrees. If I'm talking about radians, something like pi over 6. I'll just write everything in radians on the board. So could we find the wrapping function of those three angles that we said are going to be important for the unit circle? Turns out we can, using some clever applications of the Pythagorean theorem. Is that right? The easiest one is going to be the pi over 4, which is the 45 degrees. I'll show you that. If I'm going to write it in the first quadrant. I'm just going to write the picture of the first quadrant. Let's imagine this is 45 degrees. And then I draw the corresponding right triangle. Okay. This is going to have to be 90 degrees, right? It could be the x value, y value. This is going to have to be 45 degrees as well, because the angles of a triangle have to add up to 180 degrees. We all know that, right? Angles have to add up to 180 degrees. But what does that mean x and y have to be if this is 45-degree angle? This is a 45-degree angle. That means x and y have to be the same. Because this one is opposite of 45 degree. This one's opposite of 45 degrees. So this is an isosceles triangle, specifically an isosceles right triangle. Okay. So when we have 45 degrees or pi over 4, then x and y are the same. So my equation becomes x squared plus y. My equation, which was x squared plus y squared equals 1, is actually x squared plus another x squared equals 1. And I can solve that. I can take that to be 2x squared. That means x squared is a half. If I take the square root of both sides, I get square root of 1 divided by square root of 2. Square root of 1 is just 1, square root of 2 is square root of 2. And a lot of times people will rationalize the denominator. You heard that term? So that's just, you multiply top and bottom by the square root, so you don't have a square root in the denominator. And usually how people write that, if I multiply the top by square root of 2, I get square root of 2 times 1. If I multiply the bottom by square root of 2, I get square root of 2 times square root of 2, which is just actually 2. So I get root 2 over 2. So when we have 45 degrees, we know that the x value is going to be root 2 over 2. And since the y value had to be the same, it's also going to be root 2 over 2. Does that make sense? So that's the wrapping function there. I'm not going to go through the whole process with the 30, 60, 90 triangle, but I'll show you kind of where it comes from. Imagine we're at a 30-degree angle. And we draw a right triangle. So this is 60 degrees. Okay. And I want to find the x value. Let me write it over here. So 30, 60, 90 right triangles actually come out of equilateral triangles. Do you guys know that? So think of an equilateral triangle. You guys know what an equilateral triangle is? All sides are the same. And just for the sake of argument, since this is length 1 because we're on the unit circle, we're going to look at the equilateral triangle where all the sides are length 1. And I say it comes out of there because if all the sides are the same, then all the angles have to be the same as well. So it has to be 60-degree angles on everything. And if I draw a straight line from the top of this triangle straight down, hitting the base at a 90-degree angle, then what I've done is I've created 2 right triangles that are 30, 60, 90 right triangles. Notice that the hypotenuse of that right triangle is length 1. This side, because I split it into 2, has to be 1/2. This side has to be 1/2. Do you follow that? Since the total length is 1. I didn't draw this to scale or anything. It's not perfect drawing. If I had drawn it a little bit better, it would have looked a little bit nicer, and it would have been like perfectly 1/2, 1/2. Hit it a 90-degree, all that kind of good stuff. Make sense? And so what's the equation? Well, if you look at this right triangle, this side has to have length 1. So this side over here would have to have length 1/2. So the y value is going to be 1/2. And I can solve this for x. Now I solved the whole thing, didn't I? I guess I didn't need to do that, but. I take the square root of 3 on top, and then the square root of 4 on the bottom. Square root of 4 is 2, so that gives me root 3 over 2. So the x value of this is going to be root 3 over 2. The y value we've already established is 1/2. So that's my rapid function. And then if you have a 60, 30, 90 right triangle, you just reverse the roles of x and y. And so with pi over 3, you get 1/2 root 3 over 2. So these things can be established just by Pythagorean theorem on the unit circle. And then some knowledge of how we can split up equilateral triangles, some knowledge of how the isosceles triangle with 45, 45, 90 works. And once we've established that, then what you can do is you can go all around this unit circle. And if I said, let's take a wrapping function of negative pi over 6. Well, the x value, let me rewrite this. Is going to be positive. The y value is going to be negative, but it's going to be the same process, right? So if I wanted to do a wrapping function, for instance, of negative pi over 6, I just have to keep the same x value, still positive, but negate the y value. It's going down instead of up. So that's going to be root 3 over 2 and then negative 1/2. And you can do that all around the entire circle with every. With every different angle of 30, 60, 90. So take the quadrant angles and then add 30 degrees to it, add 60 degrees to it, add 45 degrees to it. And you can do that whole thing, that whole process. Okay. Whoops. So 45 degrees and the 60 degrees came from nice 45 right triangles. I've already told you this, that if you have two coterminal angles, then the wrapping function output is going to be the same. That's, again, fairly obvious. But we wrote that on the board earlier. Okay. And this is what I was saying about like the negative pi over 6. All I was doing there is projecting positive pi over 6 across the x-axis. So that just negated my y value, kept the x value the same. If I want to project across the y-axis, that positive pi over 6 angle, then we would change the x value to a negative, y value stays the same. And if I wanted to project through the origin, then I would negate both the x and the y value. Okay. So in other words, if we're in quadrant 1, the x and y values have to be positive. If we're in quadrant 2, the x value is going to be negative, y value is going to be positive. If we're in quadrant 3, the x and y values are both going to be negative. If we're in quadrant 4, that's positive x value, negative y value. Okay. So we can use the pi over 6, pi over 3, pi over 4 angles to give us all kinds of different angles around the unit circle. Okay, and we can do that in lots of different ways. So let's take a look at a couple of examples of doing that, not just the negative pi over 6 that I did, but let's take 2 pi over 3, 7 pi over 6, negative pi over 4, and 3 pi, and apply the wrapping function to each of these. And then I'll show you a picture of the circle in a second. Okay. So if we think about 2 pi over 3, 2 pi over 3. That's more than pi over 2, because 2/3 is more than a half. But less than pi, right? So we're in this quadrant. The question is going to be, what does it match up with? Does it match up with a pi over 6 or a pi over 3? Like, we're at matchup, meaning what do I project across the y-axis to get to 2 pi over 3? And the answer is the following. This is the wrapping function of pi over 3. The wrapping function point is of 2 pi over 3 is going to be here. It's going to basically be the wrapping function of pi over 3 projected across the y-axis. Now, does everybody see why that is? Let me explain it in a couple of ways. One way you can see this is that we went angle measurement of pi over 3 up this way. If I did that same angle measurement pointing left in a reverse way, this would be pi minus pi over 3, which is 2 pi over 3. I see that? So I went pi units and then minus pi over 3. So that's like pi minus pi over 3, which is 2 pi over 3. The other way you can see it is that this breaks it up into thirds. 1/3, 1/3, 1/3. Okay. But all this is saying is that the wrapping functions are going to, this wrapping function projected across the y-axis will give me the same as this wrapping function. So I look at the wrapping function on pi over 3. I saw that was 1/2 √3 over 2. Since we're in the second quadrant, I just make the x value negative. So it's going to be negative 1/2 comma √3 over 2. Everybody follow that? So I projected across the y-axis, meaning I changed the x value from positive to a negative. same height, same y value. Let's play that same game with 7 pi over 6. Seven pi over 6 shoots over there. Notice that's a pi rotation plus an additional pi over 6. So how I think of that I'll write this. Is the wrapping function of pi over 6 projected through the origin. And if I project that through the origin, I'm going to take the wrapping function output of pi over 6 and just negate the x value, negate the y value. So I go back to this one. I'll negate the x value, that'll become negative root 3 over 2, and then negative 1/2. Sorry about that. Oh, what's the next one? Oh, negative pi over 4. Wrapping function with pi over 4. Gonna be up here. Wrapping function of negative pi over 4. Gonna be down here in quadrant 4. Notice, I can draw this very well, but notice that's gonna have the same x value. So x is still gonna be positive, but the y value is gonna be negative. So that means that the wrapping function is gonna be the same output as pi over 4, just projected across the x-axis. So negate the y value. That's going to be a positive root 2 over 2, comma, a negative root 2 over 2. You see what I'm doing there? So just projecting across the x-axis, projecting across the y-axis, projecting across through the origin. All of those things can be done. And then 3 pi well, 3 pi is going to be coterminal with 1 pi. All right? So the wrapping function of 3 pi is going to be right here. That's coterminal with 1 pi. We already figured that point out. That's negative 1, 0. Okay. By the way, oftentimes books will lay out the unit circle in that exact way. They'll show you the quadrant angles along with the points where those quadrant angles intersect the unit circle. And then they'll show you the 30, 60, 45 degree angles, or the pi over 6, pi over 4, pi over 3 radian angles along with their wrapping function values. Okay. And then they'll show you all of those projected across the 4 quadrants. And if you take the angles in degrees, then you're going 0 degrees, 30, 45, 60, 90, 120, 135, 50, 180. You can see all the degrees there listed. All the degrees here listed out are shown between 0 and 360. But obviously you can use coterminal angles if you get something like 450 degrees. Or if you get something like negative 45 degrees. And the same is true with radians. Radians go from 0 radians to 2 pi radians, but if you get something other measured in radians and it's outside of that 0 to 2 pi range, then just use coterminal angles. Is that right? Now, you don't have to memorize the entire unit circle or anything like that. I don't expect you to. In fact, we're going to see right now that if we're finding other values, like what if I wanted to take the wrapping function of 22 degrees? Or the wrapping function of 11 pi over 90. That's 22 degrees, by the way. Those are the same angles. 22 degrees is between 0 and 360. 11 pi over 90 is between 0 and 2 pi. But I can't figure that out from that unit circle picture. Okay. It's still going to be some point that satisfies x squared plus y squared equals 1, because it's going to have the same, going to be on the unit circle. We know about what 22 degrees angle looks like, or 11 pi over 90 looks like. But we can't find this based on triangles. It's not going to be very nice. And so this is where we have to start using sines and cosines. One way to define sine and cosine is to define them based on the angles they make. I'm sorry. To base them on the x and y value of the wrapping function with angle t. More commonly, they use theta, but I couldn't write up the letter theta on the unit circle. Maybe I'll write theta on the board. But if you have a wrapping function with some angle theta, then the output is going to be cosine of theta, comma, sine of theta. So the x value and the y value are going to be given to you by cosine of the angle and sine of that angle, respectively. Okay. So if we look at our wrapping functions from earlier, and I focus in on that first quadrant, if I did cosine of 60 degrees, I should get 1/2. And if I did sine of 60 degrees, I should get √3/2. Or if I did cosine of pi/3, I should get 1/2. Sine of pi/3 should give me √3/2. Now, this creates kind of a problem and kind of not a problem. Get a little brighter. Weird. I say kind of a problem, kind of not a problem, because that's better. If I put cosine of 60 and then I put cosine of pi/3, what this is telling me is that right now my calculator is working with degrees in the correct way, but not with radians in the correct way. Does that make sense? So we have to tell our calculator whether we're inputting in degrees or radians when we deal with cosines, and when we deal with sines, and when we deal with the other trig functions. Everybody get that? The way you do that is you go into the mode menu and then just click on whether you are using radians or degrees. If I use radians, I click on that and then hit quit. And then I can do cosine of pi/3. This should be giving me 1/2, which it does. And then if I take sine of pi/3, this should be giving me square root of 3/2. And that is the decimal version of square root of 3 divided by 2. Okay. And if I wanted to do, for instance, cosine of pi/6, that should give me square root of 3/2. Sine of pi/6 should give me 1/2. Cosine of pi/4, we just saw, should be square root of 2/2. Sine of pi/4 should be square root of 2/2, and that is the decimal version of square root of 2 divided by 2. Okay. And then we saw on all of these other ones, for instance, we saw 7 pi/6. Remember that was the negative √3/2. Sure enough, I get the negative of that decimal. And then sine of 7 pi/6. We got negative 1/2, which is that decimal. So the cosine and the sine are working for all of the wrapping functions that we saw before. Wrapping function outputs that we've seen before. And you can go back and check all the wrapping function outputs. Like we had the wrapping function of 3 pi and we got negative 1 comma 0. Sure enough, we get that with cosine and sine. Wrapping function of 7 pi/6 gave us negative √3/2 comma negative 1/2. And we got that with cosine and sine. We get that. And now if we wanted to, even though we don't have a nice triangle to deal with the 22 degrees, we can take cosine, since I'm in radian mode, I'm gonna plug in the radian version of 22 degrees. That's 11 pi over 90. That would be the x value output of the wrapping function. And sine of 11 pi over 90 would be the y value of the wrapping function. So all of these ones that we did before, you can check out, see that they're the exact same as what we're getting now. And then we have even more power. We can say this is cosine. Again, I'm using 11 pi over 90 because my calculator is in radian mode. I'm going to go out to more decimal places just so we have it written down. But 0.9272. 3746. Again, I went down to 4 decimal places just so you have a little bit more to look at. That's all. If Moodle asks you to round to 2 decimal places, round to 2. By the way, because this is a point on the unit circle, this value squared plus this value squared should give you 1. Does that make sense? So if you took 0.9272, I know that's a rounded number, and square it, and then 0.3746 and square it, you'll get something that's very close to 1. You won't get exactly 1 because it's rounded, but if you square this plus square this, you get something really close to 1. Is that right? So cosine is the x value of the wrapping function. Sine is the y value of the wrapping function. And you can do that, excuse me. If your calculator is in radian modes, you plug in radians. If your calculator is in degree mode, then you plug in degrees. Okay. We just did basically all of this, what we're doing. Okay. Oh, those are nice. By the way, for just some practice, let's plug in these values. Let's take cosine and sine of 5 pi over 3 and cosine and sine of 7 pi over 4. I want you to get the decimal versions and then also translate those quickly, not using the unit circles, but using what you know about what square root of 3 over 2 looks like as a decimal, what root 2 over 2 looks like as a decimal, what 1/2 looks like as a decimal. Convert those to actual exact values. Does that make sense? So find the exact values of these utilizing your calculator. All right. Now, here's what I'm saying. So hopefully everybody's getting me. What I would do to find cosine of 5 pi over 3, I'd first off make sure my calculator is in radian mode, and then I just type in cosine of 5 pi over 3. When I did that, I got a 0.5 on my calculator. And I know that 0.5 is the same fraction as 1/2. Okay. When I do sine of 5 pi over 3 on my calculator, I would get negative 0.866025 and blah, blah, blah. And if you've seen this enough, you'll recognize that that is the decimal version of negative root 3 over 2. So we see that that is negative root 3 over 2 if you've done that enough. And the reason I'm pointing out this is because that's a lot faster than what we were doing before. We could have said, well, where is 5 pi over 3 with my wrapping function? And we could have said, well, that's like projecting pi over 3, the wrapping function at pi over 3, across the x-axis. If I project across the x-axis and I negate the y value, and this is telling me that the cosine would have had to been 1/2. The sine of 5 pi over 3 would have had to been negative root 3 over 2. Being able to recognize that decimal as being negative root 3 over 2 is a lot faster than using the logic of projections across to figure that out. So now I can kind of do both. If I want to find the wrapping function of 5 pi over 3, I can just plug in cosine of 5 pi over 3, figure out that it's 1/2. Sine of 5 pi over 3, figure out that it's negative root 3 over 2. And I don't have to worry about keeping track of projecting across the x-axis, or if we're over here across the y-axis, so on and so forth. The same thing would work with 7 pi over 4. If I take cosine, oh, shoot. On 7 pi over 4, I get root 2 over 2 again. I have to recognize that that ugly decimal 0.707 is root 2 over 2. And with the sine, I end up with a negative root 2 over 2. And again, that's just a little bit quicker than trying to keep track of our wrapping function. Of 7 pi over 4, and then projecting that across, again, this one would be across the x-axis. That makes sense? Projecting pi over 4 across the x-axis. Okay. Now we're going to use this Pythagorean identity a lot later on, but I wanted to point it out now that we have cosine and sine defined. Since every point on the unit circle satisfies the equation x squared plus y squared is equal to 1, that means if I take cosine of theta, since that was the x value of a point on the unit circle, and sine of theta, that was the y value on a unit circle, square each of those and add those up, I get 1. The way we write that, when you want to take cosine of theta squared, so that people don't confuse that you're squaring the theta or the entire cosine, you put the square on the cosine part, generally speaking. So this is cosine squared plus sine squared of the same angle is equal to 1. So cosine squared of an angle plus sine squared of the same angle has to equal 1. And because of the wrapping function, that's going to happen no matter what angle I put in there. This is called the Pythagorean identity on the unit circle, but just in short, the Pythagorean identity for cosine and sine. Right? And that's because it comes out of the Pythagorean theorem from the unit circle. So Pythagorean identity for cosine and sine is just that. Cosine squared of an angle plus sine squared of an angle has to be 1. Again, we'll use that a lot in general. And like I said, for the non-special angles, for the special angles, we could have used our wrapping function, but that obviously didn't help us with 22 degrees. But like I wrote earlier, we can use our calculator with 22 degrees. But as always, the big thing about your calculator, I'll remind you again, is making sure your calculator is in the right mode. If you're using radians, make sure your calculator is in radian mode. That's what I've been doing. If we're using degrees, make sure your calculator is in degree mode. Right. And then we can do all of these. Okay. We can do cosine and sine of 8 pi over 5. We can do cosine and sine of 13 degrees. We can do cosine and sine of 10 pi over 11. Anything that we want, right? Basically. Fun. This will be the last thing we do for today. So if I want to do cosine of 8 pi over 5, this is in radians, so make sure your calculator is in radians, and then just type it in. I get about 0.3090. Again, I'm going out more decimal places than I normally would, just for the sake of being a little bit more accurate, or I shouldn't say more accurate, just for the sake that you can see what's going on. And then sine of 8 pi over 5 is negative 0.9511. Since my calculator is already in radian mode, I'll move over to here and do the 10 pi over 11. Cosine of 10 pi over 11 becomes a negative 0.9595. Sine of 10 pi over 11, 0.2817. Now, if we want to do 13 degrees, I can do it one of two ways. I can either convert degrees into radians, or I can just use my calculator in degree mode. So that's the way I'm going to do it. I'm going to use my calculator in degree mode. Cosine of 13 degrees is 0.9744. And sine of 13 degrees is 0.2250. Now, one last little piece of information that I can glean from here. It's kind of what we started earlier with when I talked about what quadrant the terminal side of the angle is in. Since this has positive x value, negative y value on my wrapping function, I know that the terminal angle is going to be in quadrant 4 of 8 pi over 5. Does that make sense? Since both the x and the y are positive on 13 degrees, I know that my terminal side is going to be in quadrant 1. Everybody get that? Positive, positive. On 10 pi over 11, I had negative x value, but a positive y value. That means my terminal side is going to be in quadrant 2. So that's another way, although it's a roundabout way, of figuring out what quadrant your terminal side is in. Okay? All right, does that make sense? All right. Well, that's it for today.